This Zoom session is brought to you by the Fractal Hexwater. All right. Now, okay, we're starting on chapter 5. We finished chapter 4 last time. It's due next week. Also, I believe I've already shown, opened up the quiz number 1 for chapters 1 through the first quiz, which is available on the course modules, both in downloadable and as a module form. All right, so be with that. Now we're going to move on to chapter 5, section 1. Oh, yes, about the inbox. Please use the inbox rather than my campus email for submitting homework and quiz, because for some reason I have been unable to access that, but I'm still able to access inbox. Go figure. Oh, and Baoling Guan, thank you. I'm glad you were able to access Canvas, and this is important.
Did you receive my homework for the chapter 4? I just sent.
Yes, you did, and I can receive it. I'll grade it later when after class or maybe early tomorrow.
Thank you so much.
No problems. Like I've been saying, this major part of this class really consists of education and how to do, well, online everything, because this course is pretty much online everything. Welcome to the 21st century. We've been forced into it. Now, here we go. Chapter 5.1 is about exponents. 5.2 will be about scientific notation. Exponent is an expression of this form: x to the power n. In this case, x is the base and n is the exponent or power. It consists of starting with the number 1 and then multiplying by x n times. So x to the first power is x. X to the second is x times x. X to the third is x times x times x. X to the fourth power is x times x times x times x. These two have special names. X to the second power is called x squared. The reason being is that if you have a square with side x, then its area is x times x, x squared, or a square. X to the third power is x cubed, because if you have a cube with side x, then the volume is x to the third power, x cubed. There is no special name for x to the fourth power. I suppose it would be x tesseracted, if you're into science fiction. Let's see now. All right, that's 1, 2. Now, if you have a second power times a third power, x squared times x cubed, that's xx times xxx, that's 5 x's in a row, x to the fifth power. And you get 5 from adding 2 and 3, 2 plus 3. In general, if you have two powers of x, x to the a times x to the b, then their product is x to the power a plus b. So in a sense, you could say that exponentiation turns plus into times. Now, if instead of multiplying x squared by x cubed, you take x squared and cube that, slightly different, well, that'll be x squared times x squared times x squared. You add up the exponents, 2 plus 2 plus 2, that's x to the sixth power, and get 6 from 2 and 3 by multiplying x to the power 2 times 3. In general, then, x to the a to the power b, in general, will be the form x to the power ab. Please compare these two. Here you're multiplying two powers, here you're taking a power of a power. You multiply two powers, you add the powers, you take a power of a power, you multiply the powers. Here, let's take a product, xy, and square that. Well, it's xy times xy, that's 2x's times 2y's, x to the second times y to the second. In general, for any power a, xy to the power a is x to the a times y to the a. In a sense, then, power distributes over multiplication pretty much the same way that multiplication distributes over addition. And I'm not sure we're getting into logarithms in this course, but it's similar. You wind up with a very similar idea. Okay. Now, similar thing also happens for the next power. X to the 0. Wait, did I get that right? Hold on, let me make sure. Did I get 3? Sorry about that. I missed that. If you have a ratio to the second power. That's x over y times x over y. That's xx over yy. That's x to the second over y to the second. And in general, if you take a ratio to a power a, then it equals a ratio of powers. So exponential powers distribute over division. In pretty much the same way multiplication distributes over subtraction. So those are several rules. Now, I want to talk about dividing powers of x, but something that might happen. You might end up with 0 or negative powers. So let's try and see what that means. Suppose you have x to the n. Well, we can take out a factor of x and leaving x to the n minus 1. So if you take a ratio, then x to the n divided by x is x to the n minus 1. So if you take a power of x and divide by x, you get the one lesser power. But hold on. So x squared over x is x to the first. X cubed over x is x to the second. X squared over x is x to the first. But what about x to the first over x? Well, it's x to the 1 minus 1, which is x to the 0, but also 1. So we'll say that x to the 0 is 1. Suppose I had x to the negative 1. Well, that's 0 minus 1. So you get x to the 0 over x. That's 1 over x. X to the negative 2, that's negative 1 minus 1. So the x to the negative 1 over x, that's 1 over x divided by x. That's 1 over x to the second. And it goes on like indefinitely. So in general, we have that x to the 0 is always defined as equaling 1. And in general, x to a negative power is 1 over x to the power. So for example, x to the negative 5 is 1 over x to the 5th. X to the negative 16 is 1 over x to the 17, and so on. Now, x to the negative n and x to the n are reciprocals, so this goes the other way as well. 1 over x to the negative n is x to the n. And if we have a ratio of negative powers, then x to the negative m shows up in the denominator as x to the m, and y to the negative n of the denominator shows up in the numerator as x to the power n. Swasti, right? You just came in? Right. Anyone else just joined in while I was talking? Okay, I'll assume. Now, let's take a case if we're taking...
I did.
Mariz.
Yeah.
Thank you. Mariz, thank you. Who else? All right. I'll wait on that. So here we're taking ratios of powers of x. X to 2 over x to 5th, x to 2 over x to 2, x to 5 over x to 2. Well, when you look at this, 2 x's divide by 5 x's. 2 of them cancel, leaving a 1 over 3 x's. That's x, 1 over x to the third, x to the negative 3. Now you get negative 3 from 2 minus 5, like that. X squared over x squared, that's 1, which is x to the 0, and 0 is 2 minus 2. All right, so again, we're subtracting powers, x to the 2 minus 2. X to the 5th over x to the second, that's 5 x's divided by 2 x's. 2 of them cancel, leaving 3 x's, x to the third, and we can get 3 from 5 minus 2. In general, if you have a ratio of powers, then that's going to be the x to the difference. That's sort of like the rule where x to the a times x to the b is x to the power a plus b, is x to the a over x to the b is x to the power a minus b. I had to define x to the negative powers for this rule to work in general. So they have some examples from the book. Y to the third times y to the second times y to the second. You multiply these, so we just add the powers. X to the 3 plus 7 plus 2. Y to the 3 plus 7 plus 2, that's y to the 12th. Here we have a, b, a to the third, b to the fourth. Now, it's important to write a and b as a to the first and b to the first, and not a to the 0. It's true that there's nothing on top here, but in this case, a equals a to the 1. So all right, a to the 1, a to the 3, you add those powers, a to the 1 plus 3. B to the 1, b to the 4, you add those powers, 1 plus 4. And so you get a to the 4th, b to the 5th. Now here we have iterated powers. G to the 4th to the 5th times g to the 2nd to the 6th. powers of powers, you multiply the powers. Powers of powers, multiply the powers. So this part here will be g to the power 4 times 5. This part here is g to the power 2 times 6. 4 times 5 is 20, 2 times 6 is 12. G to the 20 times g to the 12. We're multiplying them, so now we add the powers. G to the 20 plus 12, that's g to the power 32. This uses both the powers of powers rule and the product of powers rule. You have y, x to the 5th y, all to the 4th power. Here we distribute the 4th power over both factors. G to the 5th to the 4th times y to the 4th. G to the 5th to the 4th, you multiply the exponents, 5 times 4. And so you get x to the 20, y to the 4th. Here it's starting to get gnarly. M3 n squared over 6m n to the 11th. Well, again, we write this m as m to the 1st power. So you have a 1/6, m to the 3 over m to the 1, n to the 2 over m to the 11. So 1/6, subtract powers, m to the 3 minus 1, subtract powers, m to the 2 minus 11. That's 1/6 m to the 2nd n to the negative 9, which I'm willing to accept, but the book prefers that you put negative powers in the denominator. So we rewrite this as m to the 2nd over 6 n to the 9. There. Now this one's really nasty, gnarly. X to the negative 5 over x to the 2nd, all to the negative 4th power. X to the 7th over x to the negative 8th, all to the 3rd power. Okay. First thing to do is write each of these ratios as x to a difference. X to the negative 5 minus 2 here. X to the 7 minus negative 8 here. This one to the negative 4, this one to the 3rd. Negative 5 minus 2 is a negative 7. 7 minus negative 8 is 15. So x to the negative 7 to the negative 4th times x to the 15th to the 3rd. Okay, you multiply these powers here, negative 7 times negative 4. Multiply these powers here, 15 times 3. So this factor is x to the, that times that is 28. This is 50 times 3 is 45. So x to the 28th times x to the 45th. And then, okay, you're multiplying powers. And so we add the exponents, 28 plus 45, that's 73. So you get x to the 73rd power. What a mess. Negative 3, c, d squared all cubed, times c to the minus 1, d to the minus 3 cubed. All that divided by c cubed d to the 5th. Oh boy. Well, okay, first we'll distribute the 3rd power over all this 3rd power over all these, this 5th power over these. So here we get negative 3 to the 3rd, c to the 3rd, d squared to the 3rd from this. This part becomes c to the negative 1 cubed, d to the negative 3 cubed. In the denominator, you get c to the 3rd to the 5th times d to the 5th. Okay, now some multiplying of exponents. Negative 3 cubed is negative 27. This stays a c cubed. D to the 2 times 3 is d to the 6. C to the negative 1 cubed, multiplying, gets c to the negative 3. D to the negative 3 cubed, multiply those, d to the negative 9. C to the 3rd, 5th, multiplying, get c to the 15th, and d to the 5th. All right, now here I'm going to combine in the numerator here. C cubed times c to the negative 3, that's c to the 3 minus 3. D to the 6 times d to the negative 9, that's d to the 6 minus 9. So it gets negative 27, c to the 0, d to the negative 3, all over c to the 15th, d to the 15th. All right, we're dividing, so we subtract exponents. 0 minus 15. Well, I mean, c to the 0 just cancels, so it's just, it goes away. And this negative 3rd power becomes d to the 3rd power in the denominator. And then you add exponents, 5 plus 3. So you get in the upshot, negative 27 over c to the 15th, d to the 8th. All right, here's one of these look-alike problems for 113 where we have A, B, and C. We have x, 8x and y, 8x and y, 8x and y, but -2 in different places. Here we go. 8x, y to the -2. The exponent attaches to the y to the to the y and get 8x over y to the second. Here, 8xy all to the -2, so that's 1 over all that to the second power, 8xy all to the second. Distribute the 2, 8 squared, x squared, y squared. So you get 1 over 64 x squared, y squared. That's for this. This one, negative of 8 to the -2 xy. Well, okay, there's an order of operations things going on here, namely this -2 power occurs before we take the opposite. So 8 to the -2 just becomes 8 squared in the denominator. So it's -xy over 8 squared, or -xy over 64. That's that. Yeah, okay. All right, we end this part.